If it seems like it was a long time ago that we did this, it's because it was. It was Tuesday, which seems like a long time ago. So the last problem that we did involved, wait, this thing didn't start. Here we go. We were looking at solubility problems. We were using the equilibrium constant known as KSP, which stands for solubility product constant. And we solved this problem with aluminum hydroxide solid to figure out how much aluminum ion and hydroxide ion was created in solution. And at the end of a not super complicated problem, we got that X was 2.5 times 10 to the minus molar. And that gives us the aluminum concentration, but I want you to notice that to get the hydroxide concentration, you have to multiply it times 3. I am never going to get this Bluetooth to connect today, so just hold off on that. Okay, so to summarize those kinds of problems, for solubility problems, the reaction always has solid as a reactant. So your precipitate or the solid has to be on the reactant side. The next thing is to make sure that your equation is balanced, because it's easy to forget with something like AlOH3 that you've got 3 hydroxides to every 1 aluminum. So you've got to check that. And when you do the stoichiometry and the equilibrium expression, you get terms like X when it has 1, a 1 for the stoichiometric coefficient. But if there's a 2 for a stoichiometric coefficient, you're going to get a 2x. But because you then put it into the equilibrium expression, the 2x gets squared, and that becomes 4x squared. Or if there's a 3, like there was in this problem, we got a 3x for the hydroxides, and that turned into a 3x to the 3rd power, because you raise it to the 3rd power in the KSP expression, and that led to 27x cubed. Whoops, which I was in the middle of writing there, but I didn't need to, because. So when you multiply those out, you get terms that are x, 4x squared, because the 2 is squared in addition to the x, and 27x cubed. And I can't think of anything with 4 ions in it. So I'm not writing that down. But I always found it distressing that you got a 2 because there were 2 moles of one of the ions, and then you had to square it, and so you always got a 4x squared. I'm like, it doesn't seem like you should have to use it twice. You've already done it once, but it happens in both places. Hello. I'm sincerely pushing all of my tech to the limit. Look up. Okay. So we're gonna take a quiz. The solubility reaction for barium phosphate is, we got four choices here. All right. This is all about that balancing the chemical reaction. You need to be able to write it, you need to be able to balance it. So about 10 more seconds. Okay, so majority of the people picked B. So the majority picked B, and if you look at it, this clearly says there's 3 bariums, and we got that over here. And this says there's 2 phosphates, and we got those over there. We have the solid. We have the solid on the reactant side of the equation, and so we have the majority did pick the right answer. Of course, what's wrong with letter A is the solid is on the wrong side of the equation. That's also wrong with letter D, and letter C is just doing something crazy with phosphate sub 2. This one says it's harder. For the above reaction, what is KSP equal to after forming an ice table? And those are your 4 choices. The star represents multiplication. I didn't want you to mix that up with the X's. So you have to sort of set up your ice table and figure out what you've got. Okay, about 10 more seconds. Okay. pretty evenly split between B and C. And so if you look at we've got our solid going to 3 bariums and 2 phosphates. We're going to get 3x, because there's a 3 in front of the barium, and a 2x because of the 2 phosphates. And when you put those into the KSP expression, you have to raise them to their stoichiometric coefficients. So that's going to be cubed, and the 2x gets squared. So that gives you your 27x cubed times 4x squared. So going back to that summary page a few slides ago, we always have solid as a reactant. You got to check on that it's balanced, that you have the right number of each kind of ion. And then you get these x, 4x squared, 27x cubed terms after you do the stoichiometry and put it into the KSP expression. So there's something related to the KSP problems, which is called molar solubility. And so at saturation, which is the equilibrium state, where you have the maximum amount of dissolved ions, you call that a saturated solution. And the way you make it is you put in way more solid than can actually dissolve. And so the maximum dissolves, and there's still solid at the bottom, and that helps maintain that saturation level. And at equilibrium, the rate of dissolving of the solid is equal to the rate of precipitation. And so this is harder to maintain if you don't have a lot of excess solid sitting at the bottom. And the molar concentration of the ions at equilibrium is called the molar solubility, which is given the variable S typically. And this is the amount which dissolves under equilibrium conditions. So in the problems that we have been doing, S was the same as X for those problems, because we were calculating the equilibrium amount of ions that would have dissolved, and X is for 1 mole, or for an ion that had a stoichiometric coefficient of 1. So here's a problem that's similar to an example in the OpenStax book. The molar solubility S of lead-2 iodate is 4 times 10 to the minus 5 molar at 25 Celsius. What is the KSP value? So step number one is to write the balanced equation. And this setup is great for homework and not so great for exams. It's also okay on quizzes. Not so great for exams. Anybody know why I probably wouldn't put it exactly like this on an exam? How many of you are really confident you know what an iodate ion is? So when you balance that equation, you're going to have trouble. So lead-2 iodate, it's like this. Iodate is the IO3 minus ion. It's an analog of chlorate. Right? There was hypochlorite, chlorite, chlorate, and perchlorate, and those went ClO minus, ClO2 minus, ClO3 minus and ClO4 minus. So we're looking at the analog to the chlorate ion. So this is iodate. And then that's going to make our lead 2 plus and our IO3 minus. And to balance that, I need a 2 in front there. So am I going to end up with 2x squared or 4x squared or 4x cubed or 27x cubed for my KSP? What is KSP equal to? A, B, C, or D? I'm gonna stop it. Good. Maybe 5 more seconds. People like C. It's not quite the majority of the class, but it is C. So how do I get that? So doing my ice table, I've got so much lead iodate solid sitting around. It's not all going to dissolve, but how much lead and iodate do I make? I'm going to make X of the lead and 2X of the iodate. And KSP are those concentrations raised. This one is going to go to the first power, and this one should be raised to the second power. So my KSP is X times 2X squared, and that's going to be X times 4X squared, which is 4X to the third power. So this is the part that can mess you up on solubility problems, is remembering what S is related to. S is related to X. And if you want to think of mnemonics, how are you going to think S is related to X? What word can you think of? Red Sox. That's the first thing that came into your mind, right? The Boston team. No? I can't even imagine what other word you might have come up with. Yes, so S is related to X. So, and they told us what S is equal to in the question. It's 4 times 10 to the minus 5 molar. So KSP is going to be equal to 4 times 10 to the minus 5 molar to the third power. So this problem is kind of fun because you didn't have to solve for X. They actually told you what it was in the question. It's the amount of this that dissolves, which is also the amount of lead to ion that's in the solution, because they have the same mole ratio, right? Or the same stoichiometric coefficient. And let's see what that was. Four times 10 to the minus 5, and I have to raise that to the third power and multiply by 4, and I get 2.6 I only have 2 sig figs here. 2.6 times 10 to the minus 13. And it's an equilibrium constant, so it has no units. Even though it looks like it's molarity to the 3rd power, K's never have units. Go ahead. Well, our equilibrium constants are always products over reactants raised to their stoichiometric coefficients.
So that would be this before it bound.
Right. Right. So this one has a coefficient of 1, and this one has a coefficient of 2. So that one gets raised to the 1st power, which is, you don't have to do anything, but this one gets squared. And so when you have quantity 2x squared, that turns into 4 times x squared. It's really common to write this down and forget to square the 2 and to write a 2x squared, which is why I put that answer up there. But that it's really easy to forget to square that too. So when we start with molar solubility and we're asked for the KSP, that's usually an easier problem than starting with a KSP and going back to what X is. Because one of them you're squaring or cubing and going up, and the other one you have to, and for whatever reason, taking a square root or a cube root is more of a pain. Does anybody else feel differently from that? I don't know. It's kind of like addition is easier than subtraction for some reason. All right. So, okay, so now we've kind of established what happens when you dissolve an ionic compound in water. You can figure out what the equilibrium amounts of all the ions are. If you know what the molar amount that dissolves, you can figure out what the equilibrium constant is. Now we're going to raise the level of difficulty by 1 and talk about what happens when you already have one of those ions in the solution. So we saw earlier, and by earlier, I mean like on Monday, that the amount of silver and chloride ions which can dissolve in a saturated silver chloride solution was 1.3 times 10 to the minus 5 molar. That's like the 1st or 2nd slide in this PowerPoint. So you have to back way up. So for silver chloride, the molar solubility for pure water is 1.3 times 10 to the minus 5 molar. So we started from a KSP way back at the beginning of this PowerPoint, and we solved for this. That was the amount of silver chloride which could dissolve, which also is the amount of silver ions and chloride ions present, because they all, it's a 1-to-1-to-1 chemical reaction. But what if we tried to dissolve that silver chloride in 0.1 molar sodium chloride? Does that affect what happens? Because sodium chloride has chloride in it, and there's chloride in the silver chloride. It's kind of like the problems that we did with the buffers. Right. So the initial chloride concentration, when we did the silver chloride dissolving into pure water, that was equal to 0, right? Initially, we had no silver ion and no chloride ion. But if we're dissolving in 0.1 molar sodium chloride, the initial chloride concentration is 0.1 molar. So let's find out what S is in a solution of 0.1 molar sodium chloride. Okay, so we're going to write out the equilibrium table. And what we want to write is silver chloride, solid, goes to silver plus chloride, and these are the ions, aqueous ions. And we don't worry about the concentration of the salt, the silver chloride salt, because that doesn't affect the equilibrium. But we're going to gain, and initially we have no silver, but we have 0.1 molar chloride, because that's part of sodium chloride. we're going to gain x's there, and we're going to end up with x and 0.10 plus x. Now, before we finish solving the problem, I want to ask you one question. We're just going to do predict. Will more silver chloride dissolve in salt water or less than in water? So more is A and less is B. So here's your multiple choice question. Will more silver, oh, I guess I could give you a letter C. C is or the same. Will more dissolve, that's letter A. Or less silver chloride will dissolve than in water. It's off the bottom of the chart, sorry. Or C, it's the same. Okay, I'm gonna stop it in 5 seconds. It's basically equal between A and B right now in the class. So I'm going to say one more thing and we're going to run this again. Let's say we fully dissolve our sodium chloride into pure water, okay? And then I add the sodium chloride to make it a 0.1 molar sodium chloride solution. So the silver chloride is already dissolved in pure water. So it's, what was it, 1.5 times 10 to the minus 5 molar. And then I throw the sodium chloride in there. In other words, I am adding a product. What does Le Chatelier's principle say is going to increase after I add a product? So I'm going to run this again. I'm going to say, should more silver chloride dissolve in salt water compared to regular water, or less? Or does it stay the same? Le Chatelier says it's not going to stay the same because it never stays the same with adding and subtracting things. Unless it's that pressure thing with the gases. I'm going to give you 10 more seconds. All right. Okay, I'm about to look at the results, and either I made an argument and you looked at it and you're like, oh, it's got to work like this, or I confused the heck out of you and you all took the wrong thing. So I don't, oh, it stayed exactly the same. So 6 of one, half dozen of the other. Sorry, okay. So if all this, if I have silver and chloride dissolved in pure water, and I add a bunch of this, and so we go back towards the product side, that means, will I have now less dissolved or more dissolved? I added a bunch of this, and so it goes back towards the reactive side. Do I have less dissolved or more dissolved? less. It's less. These Le Chatelier's problems, they always work in the same way, but you gotta think through the process to get to the end of it. So the answer is less. Less will dissolve. Let's work the problem now. So KSP is 1.6 times 10 to the minus 10. And that's going to be equal to x times 0.10 plus x. But my KSP is small. I expect x to be small. So I'm going to approximate, and I'm going to say that's x times 0.10. Which means that x is 1.6 times 10 to the minus 10 over 0.10, because I divided both sides by 0.1. And when I do that, I get that x is 1.6 times 10 to the minus 9 moles per liter. Oop. 1.3 times 10 to the minus 5. So in pure water, S was 1.3 times 10 to the minus 5 molar. When I added all this chloride, by adding sodium chlorides, my molar solubility drops from 10 to the minus 5 down to 10 to the minus 9. So it's a lot less that dissolves. So this is called the common ion effect. When there is an ion already in the solution, which is also part of your salt, less of that salt can dissolve. And you can reason it out with Le Chatelier's principle, or you can calculate it out with the equilibrium tables. But they should both give you the same answer, which is that less will dissolve with the ion, the common ion present. Oh, look, here's the whole problem. Just in case you like it better typed than written out. Oh, okay. So every year when I teach this, I get a little depressed because this is, this turns out to be really hard in the sense that I know the class does not perform well on it. So whatever the characteristics of this problem are, people don't get to the end of it and come out with the right answer, typically. And I think it's because it's equilibrium and it's Le Chatelier, and there's a bunch of stuff in there with dilution as well. So what happens if you have two salts or two solutions of salts and you're going to mix them together and they could make an insoluble salt? In other words, there could be a precipitation that occurs. Can you predict whether or not the precipitation will happen based upon the KSPs of all the salts that are involved? And of course, the answer is yes, you can do it. The hard thing to remember is, okay, reactants are always the solid in solubility problems. The products are always ions. So if your Q is bigger than K, then you're going to go towards reactants, which means you're going to make solid. So that's what says precipitation. Q is bigger than K, and so you're going to head back towards reactants. When Q is bigger than K, you go this way, and reactants are always the solid. So that means that the ions precipitate. The problem is getting the concentrations of your ions in the first place. And if you look at the top there, there's I'm pointing out exactly where to go in your book to find this issue. So here's a problem. Here's a sample problem. Suppose I mix 50 milliliters of 0.05 molar lead nitrate and 50 milliliters of 0.030 molar potassium chloride. Will the lead chloride precipitate? It has a KSP of 1.6 times 10 to the minus 5, which is fairly large for a KSP. I mean, a lot of them, we saw one that was what, 10 to the minus 97. So this is on the bigger side. But we need to figure out how much, what are the concentrations of the lead and the chlorides that are present in this final solution? And will it give us a QSP bigger than the KSP? So first of all, let's write out the equation for lead chloride. When you balance that, I was nice enough. Look, here's the formula. But you do need to know that chloride is not a Cl2 ion, it's a 2 Cl minuses. And then the KSP expression, which is the same as the QSP expression, is lead ion concentration times the chloride concentration squared. Because there's a 2 in front of that chloride, it's going to be squared over here. But let's find the concentrations. They are not 0.05 for the lead and 0.03 for the chloride, because I have 50 mils of one, 50 mils of each of the other, and when I mix them, what's my final volume? 100. You guys know that when you go from one volume to a larger volume, that's called dilution. When you mix two solutions together, all the ion concentrations get diluted, because now all of a sudden there's all this other liquid that they're combined with. So if I have 0.05 molar lead 2 plus in my first solution, that's my initial molarity. I'm going to multiply it by my initial volume over my final volume. Right, you guys typically memorize this equation for dilution, M1 V1, it's hiding. M1 V1 equals M2 V2. I don't like that version because it tricks you into thinking something different about how we usually, in the lab, we think about dilutions as the volume over the volume, and then multiply that by the concentration. How much is my concentration changing? It's volume 1 over volume 2. So I started with 50, I'm going to 100. So that's 50 over 100. That's just dividing by 2. Let me write it out. 0.050 molar times 50 milliliters over 100 milliliters is 0.050 molar. 50 over 100 is just a half, right? And what we tend to say in lab is it's a 1 to 2 dilution. You just take the molarity and divide by 2. So the final molarity of my lead 2 ion is 0.025 molar. And then 0.030 chloride is, again, it's 50 over 100. So that's 0.015 molar chloride. So shadow. Here we go. M1V1 equals M2V2. That seems to be the way everyone memorizes the dilution equation. I don't know. Does everyone remember that equation? I don't like that version. I like this version. M2, that's what I'm looking for. My final volume, my final molarity. It's the original molarity times the ratio of the volumes. Sometimes if you rethink about it that way instead of the first way, dilution becomes a little more clear. Or not. If you liked it better the other way and you can work the problems that way, you can ignore me. But people tend to talk about a 1 and 2, a 3 and 10, something like that when they talk about dilution in lab. Okay, so now let's work this QSP problem. QSP, well, I want an undo button here. I really don't like, just happened. I really don't like the fact there's no undo button. All right, my QSP is my lead concentration, and we figured that out over here, 0.025. And it's my chloride concentration squared. So what is that equal to? Oh, I have 1 minute. I was going to say, let's do it as a short answer, but let's not. Let's just get the answer real quick. I get 5.6 times 10 to the minus 6. Remember, the question that we're actually asking here is not what is QSP, it's will the lead chloride precipitate? Here's our QSP, 5.6 times 10 to the minus 6. To get it to precipitate, our Q needs to be bigger than the K. And we just got a Q that was less than K. So the direction towards equilibrium is towards more ions. That means more ions have to dissolve to reach equilibrium. So we do not get a precipitate in this question. And the reasoning is that Q is less than K. And that sounds like the end of class to me. Oh, goodness. I got a lot of stuff to grade from you guys. And I also have a lot of stuff that I'm grading for my senior class. And that is making me go like super slow. It's like both of y'all had exam 2 last week. And you also both had an exam 1 makeup this week, because both classes are having a little bit of struggle compared to what typically happens in my classes. So I'm hoping that exam 2 was a little bit more of a confidence thing for the class after exam 1. And I'm looking forward to finalizing those before the end of the weekend. We'll see what happens. When I get some scores, they'll go up on Blackboard. I don't think I can hand them back because I still have a few people who had illness or other issues, and I need to deal with them. And I really don't want to write another exam too, because those things take a long time. But hopefully you'll have your score back, if not the exam itself, by Monday. All right, have a great weekend. Looks like we got some nice weather out there. Hope you can get out and enjoy it. Planning to be on my bicycle tomorrow. Get a couple miles.
Dr. Reeves.
Yes.
So I was on this entire time, but my clicker wasn't allowing me to participate. Like I sent you an email of like the picture, and it's like it wasn't allowing me to click on it, like any of the answers.
Okay, that's really weird. I don't know.
Yeah, I don't know if it's like the connection, but every time I clicked on it, it just said failed to send. And I was just like, what am I supposed to do? I didn't want to interrupt you during your.
Yeah. Usually that's a thing where you go out and restart it, like log out and then log back in. Did you try that?
I tried to log out and then log back in, and it still kept doing it. So I was just like, well, do I need to turn my phone off? I had the Zoom on. I was just like, okay, what's happening?
I don't have a good answer for that, especially if you're doing what you normally do, and usually it's fine. So I guess you did send me an email, right?
Yes, I sent you an email.
Okay.
And
So
then I also sent in the email, it's like something else that I wanted to address, but you'll see it. It's okay.
Okay. All right. I'll try to get back to you later today.
All right. Thank you.
Bye, Sydney.
Bye.
Anybody else got a question? If not, I'm going to go ahead and shut down. All right. Bye, everybody.